Okay, and now for the moment of truth, I'm going to share my screen. Okay. Okay. Okay, great. So let's get started. Welcome, everybody.
Wait,
so today we are going
Professor, make sure you spotlight video for your computer as well, so that the recording has your face.
Okay, so okay. I do here. Do I go? So where do I find that?
On your computer, if you hit like to the top right of your face, there's like a little ellipsis there. If you click on that, you should have an option to spotlight video. Yeah.
I did it, so okay.
Okay, great. Okay. Okay, excellent. All right, so let's. Okay, great. Thanks. All right, so so let's see. Today we're going to continue with the fast Fourier transform. Okay, so so you know it was as you remember, FFT is sort of it's one of the great algorithms, and it's probably the canonical divide and conquer algorithm. So it really fast. You know, if one covers it really fast, you see it as one object. So we did that last lecture. You know, we went through the entire.
Umesh?
But there's a lot of.
Umesh?
Yes.
Sorry to stop you so soon. It seems that the audio is not that good. Maybe it will work better without the Bluetooth. I don't know.
I don't know. Is your phone connected to a different network than it was last time? Or maybe like last time it was on data and this time it's on a Wi-Fi, or vice versa?
So it is on the same one. Let me try switching and seeing if it's any better. Let me try switching the Wi-Fi. Okay. We're on different Wi-Fi. Oh no, but it's not even.
I think because you've switched, it's completely disconnected now. I don't know if it needs time to reconnect or... Oh, really?
Yeah, so I think from the chat, it seems that people cannot hear, and I also cannot hear.
Okay, how does it sound now? Can you hear me?
Yes,
it sounds good.
Is it okay?
Yes, I think so.
I'll let you know. Like.
Oh, all right. So let's continue. Okay, so I was saying about the FFT. You know, so what we did last time is when we went through all of it, we saw how to do the FFT, but there were quite a few loose ends that I left just to be able to go through the entire algorithm. And so today what I'll do is I'll tie up all the loose ends. You know, we, for example, didn't see how to do the inverse FFT. And so, you know, what I'll do is show you the FFT also from a different viewpoint so that you get a comprehensive view of the entire subject. Okay, so let's start. Let's remember what the FFT is. You know, so if we have a polynomial a of x of degree n, so it's a naught plus a1x plus dot 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 plus a n minus 1 x to the n minus 1. then the vector, an n-dimensional vector.
So I don't think we can hear you again.
An n-dimensional vector whose entries are the relation. And then we said, there's another way to represent this polynomial. And the other way to represent this polynomial is by representing its values at n distinct points. So we pick n distinct points, and we write out the values at these n distinct points. And so we pick, at values x0, x1 through xn minus 1. But now for the Fourier transform, we choose these values very carefully. And we choose these to be the roots of the nth roots of 1. Okay, so the n complex numbers which are solutions to x to the n equal to 1. Right? And so we have n solutions which are 1 omega, omega squared, omega to the n minus 1. Right? So now what we'll write out here is a of 1, a of omega to the n minus 1. And so the transformation that takes us from the left to the right, is Fourier transform, and then us back from the values to this coefficients. And there were 2 points to this. One was that we can do the FFT and the inverse FFT in order n log n steps. This was a really big deal. This is a very fast algorithm. The polynomial is very fast. So if you're given, if you want to do polynomial multiplication.
Umesh, you are still cutting off.
So if you're given the polynomial a of x, yes.
Umesh, can you hear me?
Is there a problem?
Yeah, so
yes.
you're cutting off
So we're just
a lot. Andrew? Yeah.
Ah.
Yeah, you might want to consider, I think it was the second lecture, you used your phone to dial in instead. The audio quality was slightly worse, but I think it's a little bit more reliable just because it's not using the internet. So you might want to try that.
Okay, so let me try it.
It seems like your phone is connected, but it's muted right now. You might need to unmute it either through Zoom or through your phone itself.
I just copy what they gave us.
Professor Paul, I don't know if you are able to unmute his, there's one instance of him that has like the little phone icon. I don't know if you're able to unmute him from your end.
I'm trying to unmute him, but it's not working. And where'd he go?
Let's see. Umesh, I think now the phone is not connected. Could it be? I see only your video.
Okay, how's this now?
This sounds good.
Okay, let's go with this. I'm hoping that I've placed the phone at a place where there's better reception. So let's keep our fingers crossed. Okay, so let's see. So so far I'm doing reviews. So I'm just saying, if you want to multiply two polynomials, what you would do is go from the coefficient representation, which is what you're given, the coefficients of A and B, move to the value representation. And then in the value representation, the value of C at 1 is just A of 1 times B of 1. So computing the values at all these points will just take you order n time. And so the total time required to multiply the polynomials is just the time required to do the FFT, do the pointwise multiplication. So that's n log n, order n, and then go back, which is order n log n, right? So now, of course, there are two things you have to be, one thing you have to be careful about. If the polynomials are of degree n, then the product is of degree 2n. So you'd better start off with writing A as a 2n degree polynomial, which you can do by just putting leading zeros for coefficients. Okay, you just pad it out. The other thing you might want to think about is that what we are making use of here is something that, if you've seen Fourier transforms before, is the convolution multiplication property of Fourier transforms. When you're doing multiplying polynomials, it's like a convolution. In the Fourier domain, it becomes pointwise multiplication. And so that's much cheaper, right? So as long as we can do the Fourier transform easily, then that's a good thing. Okay, let me do one other thing very quickly, since some of you were, it was a little confusing for you. So let's do it. quickly, which was the signal processing application. So so in signal processing, one of the most fundamental things is a linear time invariant system. What's a linear time invariant system? So it's a box where you give it some input. So you have some input, and your input is something that varies with time. It might be a sound, it might be music. So your input you can think of as some signal, right? And what we're going to do is discretize this signal. So we just discretize its values at various points. And so let's call this signal A. And so these discrete values we are going to call A of 0, A of 1, so on up to A of n minus 1. Okay. And now, what about this linear time invariant system? Well, this linear time invariant system has the property that if you feed in a signal of 1 at time t equal to 0, then the output is b0, b1, ... bn minus 1. So that's what this is called the impulse response. And it's, so let me write this down over here. The impulse response of the system is also some, it's some function which we also discretize, and this is now b0 through bn minus 1. This was a0 through an minus 1. And now the fact that it's a linear time invariant system tells us that this is enough to tell us what the output is. So what does it mean, linear time invariant? Time invariant says, suppose we, instead of giving an input of 1 at time 0, we give an input of 1 at time 1. What's the output? Well, the output is just the same output, b0 through bn minus 1, except it's shifted by 1, right? So now b0 becomes 0, b1 becomes equal to, the output at time 0 becomes 0, output at time 1 becomes b0, at time 2 it becomes b1, and so on. Okay, linear, and then linear says if you give twice the input, then you'll get twice the output. If you give the sum of two inputs, you'll get the sum of the two outputs. Okay, and so basically, if you look at this and you ask, well, first of all, let's think of this input as the polynomial a of x. Let's think of this response as the polynomial b of x. Okay, and so now we want to understand what's the output. C0, C1, C. Well, it turns out the output is going to go on for longer, right? So it'll go on for roughly 2n or 2n minus 1 steps, right? It'll go on for, so the inputs were lasted for n steps, but since the input continues and the output sort of continues for n steps beyond, so it'll go on for 2n steps. And it turns out that in fact, this output C of x is just going to be exactly A of x times B of x. Right? Okay, because it's going to be equal to A0 times B of x, because that the input, oh, sorry, I gave you two different notations. Let me just rewrite this. This was A0, A1, A sub n minus 1. So our input at time 0 was A0. So the output is going to be the impulse response, which is B of x, but it's going to be scaled up by A0. Our input at time 1 was A1. And so the output is going to be B of x scaled by A1, but it's also going to be delayed by 1 unit of time, right? And so if we write out a polynomial, except shift it right by 1, that's like multiplying by x. And so it's going to be that. And so on. Right? But if you look at what this is exactly a of x times b of x. Okay? And so you can see that if you're trying to compute the output of a linear time invariant function, a system, then that's exactly multiplying two polynomials, which is what FFT allows us to do quickly. Okay, so let me stop here for questions, and then we'll continue since we have had so much trouble getting started. So let's stop for a couple of questions, and then let's keep after that. So everybody okay with this? This was basically a review. Okay, so let me keep going now. So let me now just, since last time I sort of spoke about these nth roots of unity very quickly, today I'm going to just spend a few minutes talking about what the nth roots of unity are. Okay, so all right, so hopefully you've gone through this already, and before you've also refreshed it in your minds, but let's just go through just to make sure. Okay, so we are looking at the n complex roots or solutions of the equation x to the n equal to 1. Right, so there are exactly n such solutions, and these are complex numbers. So let me just review what the complex numbers look like. So remember, there's the real line, and then the imaginary axis. Imaginary numbers we think of as being completely unrelated. So we can plot them orthogonal to it, so along the imaginary axis. And out here, let me map 1, 0, -1. And then this is the imaginary number I, minus I. And now, an arbitrary complex number is just a point in this complex plane. And you can describe it in two different ways. You can write out x, y as its coordinates, in which case this is the complex number which you can write as x plus I, y. So that point represents x plus iy. That's the complex number. There's another way you can write the same complex number. You can write it in polar coordinates. So what do we mean write it in polar coordinates? So you think of the line connecting it to the origin. And so the length of this line is r. And this angle is theta. Okay? So you could also write it in polar coordinates as being, the other way of writing it is as r comma theta. Okay. And so if you want to write it in the, in the same notation, right? Then this would be equal to r times cosine theta plus I times r times sine theta. And now there's very nice notation in which you can write this down. This notation just says, you can sort of write it as r e to the I theta. Now, you may look at this notation and you might say, I really don't like this notation at all. Okay, but the secret to good notation is it should make your job easy for you. So if I take two complex numbers and I want to add them, so suppose I want to take x plus I, iy, and then I want to add to this complex number u plus iv, then it's easy, right? It's u plus x plus I v plus y. Okay, so that's easy. But what if you're given two complex numbers and you want to multiply them? In this notation, if you want to add, it's easy. If you want to multiply, it's not so easy. I mean, it's not hard, but it sort of takes a little bit of work. But now, if I instead give you two complex numbers in this polar coordinates, so if I give you r e to the I theta, I want to multiply it by r prime e to the I theta prime, then the answer is just r times r prime e to the I theta plus theta prime. Okay, so it's good notation. What's the meaning of e to the I theta? It's just cosine theta plus I sine theta. Okay, but the nice thing about this notation is it allows you to do things easily that come naturally, right? In a sense, this is what data structures do for you in computer science. A good data structure allows you to do, the natural operations very easily. Okay, so multiplying complex numbers is very easy. All you do is multiply the magnitudes, r by r prime, and you add the angles up. Okay, so once we understand this, we can understand now what the n complex roots of 1 should look like. Because if x to the power of n is 1, that means that, so if x equal to r e to the I theta and x to the n equal to 1, that means r to the n must be 1 and n times theta must be equal to 2 pi or 0 or some multiple of pi, right? Okay. Sorry, let me write this slightly differently to make sure that you understand it. It must be the case that must be a multiple of 2 pi, right? Because we want to get back to 1, so we can go around the circle as many times as we want. But if theta is a multiple of 2 pi, then we are back out here. Is that clear? Okay, so now where are these nth roots of unity? Where do they sit? Well, let's make up our complex plane again. This was +1, this was -1, this was I, this was -I. These all sit on the unit circle, right? So, oops, okay, I'm making a hash of it. It's easier to draw a circle if you first draw a circle and then figure out which points it goes through. So we're just going to do that. Okay, so here's our unit circle. We know that all the nth roots of unity must lie on the unit circle. R to the n is 1, means r equal to 1, right? It's just a real number, plus or minus 1, and theta must be, it's a positive real number, so it must be 1. And now theta must be some submultiple of 2 pi, it times n must give us some multiple of 2 pi. So theta equal to 0 obviously qualifies. Theta equal to 2 pi over n also qualifies. So this we're going to call omega, right? And then we can go to 2 theta and 3 theta and 4 theta and so on. And so if we just look at, if you take 2 pi over n and all its multiples, then this gives us n possible values of omega. And these are so this gives us omega squared, omega cubed, etc. up to omega to the n minus 1. And this was omega to the 0. Okay. So those are your nth roots of unity. Okay. Now there's one other thing we are going to use. We are going to always have n even. And when an n is even, that's sort of the situation that I drew here. And then omega to the n over 2 exists, right? N is even, so you can think about n over 2. And so this -1 is omega to the n over 2. Right? Okay, so now what we can say is when n is even, the roots of unity come in pairs. If we have omega to the k over here, then right opposite it on the other side, there's going to be omega to the n over 2 plus k, which is going to be minus omega to the k. Okay, so these roots come in pairs, which are opposite each other, right? They're antipodal points. For every omega to the, for every root, there's minus of that root, which is, if it's omega to the k, it's omega to the n over 2 plus k. Okay, so we have omega to the n over 2 is -1, and we can pair up the roots. Omega to the n over 2 plus k is minus omega to the k. The other thing we can say is omega squared is a primitive n over 2th root of 1, right? Because this is e to the 2 pi I over n by 2. Oh, well, I don't want to confuse you by writing it down. It's just a n over 2th root of unity. Okay. So in fact, what we are saying is, if you were, and the other thing we can say is if you take these two roots, omega to the k and omega to the n over 2 plus k, and you square them, right? So if you square, then you get both of them become omega to the 2k, right? Because when you square this, you get omega to the n plus 2k, but omega to the n is 1. So the roots get paired up, and when you square, you get half of them, right? Both omega and minus omega both map to omega squared. So these are the properties that we'll need of these roots of unity when we are doing the FFT. Okay. All right, so now let me describe the FFT, but directly in terms of evaluating the polynomial A at these roots of unity. Okay, so the FFT, what we want to do, we are given A of x, which is we are going to think of n as a power of 2. And now we want to compute A of 1, A of omega, all the way to A of omega to the n minus 1. The omega is e to the 2 pi I over n, right? Cosine 2 pi over n plus I sine 2 pi over n. Okay. So here's the idea. So suppose, let's do an example. Suppose A of x was 1 plus 2x plus 3x squared minus 5x cubed. Okay. So what we're going to do is break this up into two parts. We'll let the even powers, we'll separate out the even powers, which are 1 plus 3x squared, and the odd powers, which are 2 okay, Okay, so I'm taking the odd powers and I'm dividing by x because they all include at least one power of x, right? So I'm just taking it, and do I want to divide it out? Maybe I don't. Maybe I just want to write it as 2x minus 5x cubed. We'll see if this is what I wanted to do or not. Yeah. Okay. So
You didn't have to do any more math classes.
I'm sorry. I think I do want to divide it. I think it's nicer if I do divide. I'm sorry?
It just takes.
Sorry, I think you're unmuted. If you could mute yourself. That would be lovely.
Okay, so I'm going to write a of x as a even of okay, sorry. So let me just simplify it out, and then so I'm not going to call this a even. So that's what I'm, so I just want to not name these for now. I want to separate out the even powers and the odd powers. Okay, so I have the even powers and the odd powers. Okay, so I've separated out this versus that. Okay, and now now I can write this. Okay, so I want to so let me do this in general, and it might be easier, and then we'll work through this example. So I want to write a of x as I want to separate out the even parts and the odd parts, and I'll write out the even parts as a sub even of x squared plus x times a sub odd of x squared. Okay, so I want to write a sub even of x squared is that, and a sub odd of x squared is 2 minus 5 x squared. Okay, so now I can write a of x as a sub even of x squared plus x times a sub odd of x squared. Right? And now if I let x squared equal to y, then what I have is a of x is is a sub even of y plus x times a sub odd of y. But the degree of this is half as much as it was before. Okay. So now what's the point of all this? So once you write it out this way, if we want to compute both a of x and a of minus x, okay, then what do we have to do? Well, a of x, as we wrote, is a sub even of x squared plus x times a sub odd of x squared, and a sub minus x is just a sub even of x squared, right? Because x squared is the same regardless of whether you're coming with a plus or minus x times a sub odd of x squared. Okay, so as a function of x squared, in order to compute a of x, all we have to do is compute a sub even of x squared and a sub odd of x squared, and then just add and subtract, multiply by x and add and subtract. Okay, so we are computing A at 2 points, right? A of degree n at 2 points. We are reducing it to computing A naught, A1 of degree n over 2 at 2 points. Okay, plus big O of one more steps. The big O of 1 steps are, we first compute A naught of x squared, A e of x squared, A even and A odd of x squared. And now we just multiply each of these by this by x and either add or subtract. Okay, so that's a constant amount of work. And so that works as long as the points that we have, we can pair up as plus and minus. And that's why we chose these nth roots of unity, because we can pair them all up as plus and minus, right? And so the time required to solve this problem for polynomial of degree n evaluated at n points is 2 times the time required for polynomials of degree n over 2 to be evaluated at n over 2 points, right? Because the x squareds now, when you take 1 omega squared omega to the n minus 1, you square them. Remember, you get these collisions. Omega to the k and minus omega to the k both square to the same value. So you get half as many points you need to evaluate at. Okay. And then you're also doing order n extra work, because for every pair you're doing a constant amount of work. There are n over 2 pairs, so you're doing constant times n amount of work. Okay, but now we need to make sure that when we are doing this recursion, we actually have we are actually solving the same problem of size n over 2. Why is it? Well, the reason is because we started with a polynomial of degree n. Now, we ended up with 2 polynomials, this one and that one. Each of them is of degree n over 2 because it's a polynomial now in x squared. It's a polynomial in y equal to x squared, right? And so if the degree in x is n, the degree in y is just n over 2. But then we are also evaluating each of these at n over 2 points. Which are the n over 2 points? It's the squares of 1 omega squared omega to the n minus 1. So what are these squares of 1 omega squared and so on? Well, when you square them, you get every other point. So you get 1 omega squared omega to the 4th omega to the 6th and so on. And these are the n over 2th roots of unity. And so we are actually reducing a problem of the same kind. And so it takes t of n over 2 steps. And so that's what gives us the recurrence. T of n is order n log n. Okay, so this is just a different way of looking at the same algorithm we saw last time. Okay, and this is the reason why I'm trying to do it somewhat quickly, just to make sure that we can just draw a connection without, but you've already seen this in a different form. Okay, so any questions?
Could you show us an actual point of the pairs and how they end up as the same value of
yeah, okay, so let's see, let's run through this example. Okay, so what are the points at which we'd be evaluating it? So we have, it's a polynomial of degree 3, meaning we have 4 points we should be evaluating it at, right? So we evaluate it at the 4th roots of unity, which would be I squared, which is minus 1, I cubed, which is minus I, and I to the 0, which is 1. So 1 I minus 1 minus I, right? Okay, so how do we do this? Well, we say to ourselves, we should be evaluating A sub even at the, at the second roots of unity. So we should take A sub E, which is 1 plus 3 times y. Okay, so I'm just going to write it as a different variable for convenience at the second roots of unity now. Plus 1, minus 1. And A sub odd of y, which was 2 plus 5y at plus 1, minus 1. Okay, so okay, sorry. So let's actually work through it more slowly. So suppose we were trying to do, suppose we were trying to evaluate it at, at these 4 points, and let's pair them up. So let's say we wanted to do this at I, comma, minus I, and at 1, comma, minus 1. So let's pick one of these pairs. So let's say we wanted to do it at I and minus I, right? So how do we do it at I and minus I? Well, we say we want to evaluate A even and A odd at y equal to x squared, which is I squared is minus 1, and so is minus I squared. So we want to evaluate both of these at minus 1. So how do we evaluate these at minus 1? Well, this, so A sub E of minus 1 is minus 2, and A sub odd of minus 1 is 2 minus 5 is minus 3.
Professor?
Okay. Yes.
I think you switched the signs in the A sub odd. In the original problem, it was 2 minus 5y.
Oh, I'm sorry. Yes, you're right. Okay. So it was 2 minus 5y. And so A sub odd of minus 1 is now, at minus 1 is now 7, right? Is that correct? Okay, so now we can go back and say A of I was equal to A sub E of minus 1 plus I times A sub O of minus 1, which is minus 2 plus I times 7. And A of minus I is A sub E of minus 1 minus I times A sub odd of minus 1, which is just minus 2 minus I times 7. Right, so now, even at this level, you can see that sharing that computation was helpful, because we could just, once we got here, we got the answer. We just read off the answer for both of these, right? Because we had it in the correct form. And so now, as you go down the recursion, you just save more and more work in doing this, because you're just doing the same work. You're sharing the same work across these different evaluations. Does that make sense? Sorry, did that answer your question?
Yeah.
Okay. Okay, great.
Oh wait, so is A sub E, so wait, how do you choose A sub E again? Is that all the odd powered polynomials?
A sub E was all the even powers, right? So it was 1, x squared, etc., x to the 4th, x to the 6th, and so on. So here it was 1 plus 3x squared.
Oh, but then when we plug in x squared into there, doesn't x squared and x squared is x to the 4th?
No, so we said we plug in x squared in there. What was x squared? X squared was minus 1, right? So we just plugged in. So I wrote this down as y equal to x squared. You know, just to emphasize that it's now degree 1.
Okay, thank you.
Some more questions?
So we pick omega and then you do omega to the 0, 1, 2, 3 to the n minus 1. We pick every
Yeah.
other one and then we plug it into it, right? So
So
because
yeah. So what we are doing is we want to plug in all of these, right? We want to evaluate all these n. But then what we realize is that we can pair them up, right? We can pair up omega to the k with omega to the n over 2 plus k because they are minus of each other, right? And so here we said I squared, sorry, I is negative of I cubed. And I to the 0 is negative of I squared, right? So we pair them up. So we pair I with minus I, 1 with minus 1. So now I picked out this pair, I and minus I. So we want to evaluate the polynomial at I, x equal to I, and the polynomial at x equal to minus I. To do both of these, what we said is, all we have to do is evaluate these even and odd polynomials, which are of half the degree, at the square, right? But the square of both of these, I squared is equal to minus I squared. Both are equal to minus 1. So we are evaluating both of these polynomials at minus 1. Right? So that's what I did here. I said a even of x squared is 1 plus 3x squared. X squared was minus 1. So that's what I call y. So it's I'm looking at this polynomial 1 plus 3y at y equal to minus 1. Okay, so what is that? It's minus 2. Similarly, this other polynomial at y equal to minus 1, it's 7. Okay, so then I'm saying we go back and we say, well, a of x was a even of x squared plus x times a odd of x squared. So now we have these two values, x equal to I and x equal to minus I. So we plug them in and we get a of I and a of minus I. But now both in terms of exactly the same polynomials. Right, so we don't have to recompute these. You know, these two polynomials are the same. These two are the same. You know, being evaluated at the same point. So we don't have to recompute them. We managed to do the, you know, to share that computation, and that's the point in FFT. Right.
Professor, does using complex numbers slow down the arithmetic in any way, or is it exactly as fast as regular computation?
Well, okay, so if you're using complex numbers, it'll obviously slow you down by a constant factor, right? If nothing else, because you have two real numbers to keep track of. So in that sense, it'll slow you down. But then you're speeding up from n squared to n log n, right? And that's a big win. The other thing that hopefully you'll get to in this homework is you can also, you know, if you don't want to use complex numbers, you can also get away with modular arithmetic. So all we need is these two properties of omega. One is that these are all, you know, you know, when you raise to the nth power, you get 1. And the second property we want is that they come in pairs. And when you square them, you get n over 2th root, you know, roots of unity. So you can achieve this in modular arithmetic, and then it's like regular arithmetic, right? So it's much easier.
Professor, do you have to pick omega as the primitive nth root of unity, or can you pick any nth root of unity?
No, you couldn't pick any nth, right? It has to be an nth root of unity, which is not also an n over 2th or, you know, n over 4th root of unity. So it's got to be that the smallest power to which you can raise it, which gets you 1, is n.
Okay.
Professor, do you think you could go over like what the next like recursive step would be?
Oh, that might be a bit painful here. So Ted, give me a sense of what would help, why you asked the question, and maybe I can narrow it down further.
I'm just kind of confused on like how it would branch out to like yeah, just like how it would branch out more.
How would you branch out more? Okay.
Yeah.
So let's go to the next level. So now, eventually, okay, so we'd be down to a sub. We want to compute a sub e of y at y equal to -1. That was one thing we wanted. And we also wanted it at and y equal to +1. Okay, so once we do this, we'll need to compute this at plus and -1. Okay, so now of course it's small enough that we can just plug it in, but we could also just split this apart into the even part, which is 1, and the odd part, which is 3 times y, right? And then we want to evaluate both at these 2 points. So we would, we'd write the 2 polynomials as 1 and as 3, right? And we are evaluating these at y squared, both of which are 1. But of course, these polynomials are now constant, so evaluating at y squared makes no difference. The answer is always 1 and 3. And then we combine them together. So we are already down at the base level of the recursion, and it's sort of more. I mean, you can follow it out, but it might be a little confusing at this level because it's so trivial. Right? Does that make sense? But does this maybe answer your question about where we would go next?
Yeah, that makes sense. Thank you.
Okay, sure.
Umesh, there was a question in the chat that I thought was kind of interesting. They were asking, it seems that you were sort of saying, you need the n to be even.
Yeah.
But we also said at one point that n should be a power of 2. So why can't you just use the fact that n is even?
Oh, yeah, good point. So remember, we started with a problem where we had a polynomial of degree, we had of degree n-1 evaluated at n points, right? We needed n to be even, but then when we recurse, we'll get a polynomial of degree n over 2 minus 1 evaluated at n over 2 points, right? But now we want n over 2 also to be even, to apply the same algorithm recursively. And then we'll move, we'll go from n to n over 2 to n over 4, and we'll again want n over 4 to be even, right? And so what that means is that we want n actually to be a power of 2. Okay. Any other questions?
So in this scenario, or like let's say we're in a scenario where n is not a power of 2, are we going to do what you mentioned in the first lecture where you just pad it with like the leading terms with coefficient of 0 until we hit that power of 2?
Exactly, yes. So we can just assume without loss of generality that we have a polynomial of degree power of 2 or -1, right? So because we just pad it out with leading zeros.
And in terms of working out this recursion by hand, should we work down to the level like you did on the bottom left, where we're left with those constants 1 and 3? Or like once we're at that linear stage where it's just 1 plus 3y, can we compute that step manually and consider that to be simple enough?
So I'm a poor person to ask about these things because I usually work things out until I know that I understand it. So okay, the true answer is you should do it till you understand understand what's going on. Now, how do people grade it? I don't. This is Okay, so I would just leave it at this point, you know, because it's maybe you should just work it out with your TAs or something. You know, so from my viewpoint, an algorithm is about understanding what's going on, you know, and the proof and so on. And you know, the reason to work through the steps is to really reinforce your understanding. You know, once you have a picture of it, that's what you're looking for in working through an example. So, you know, that's from my viewpoint, that's all you need to do.
Okay, thank you.
Yeah.
Can I add one thing that might be
Yeah,
useful?
of course.
So one thing that you can say is that you are doing things by sort of recursion, right? So you can sort of say, let's assume that the algorithm works correctly on inputs of length n over 2. And let's see that now it works correctly on inputs of length n. So if you show that, then you prove that the algorithm works, right? So you don't need to really do all these, you know, unwrap the recursion. You just need to sort of prove by induction that it works.
Yeah. Okay, so now let me go on and you know, try to take care of a few loose ends here. So one of the loose ends we had was, we said you go from, you know, from your representation A0, A1, AN minus 1, you know, you use the FFT to map to A of 1, A of omega, A of omega to the n minus 1. And how about the inverse FFT? Okay. So let me try to explain to you how that goes. And I'll just tell you mechanically how it works, and then I'll give you a picture of how it works. And hopefully the two together will help you understand how it goes. Okay, so first thing I want to do is I want to go back to the matrix notation we did last time. Except now we are going to sort of, I'll also tie it together with what we just talked about. So remember in the matrix notation, what we did was we said, well, you know, if you have A0, A1, AN minus 1, and you want to compute A of 1, A of omega to the n minus 1, the way you would do it is you'd multiply by this matrix 1, 1, 1, 1, omega to the n minus 1. Okay, so you do this, right? But remember what we said. We said, look, okay, so first of all, this is a matrix whose ijth entry, so whose j kth entry is just omega to the jk. And then we said, look, if you want to understand the symmetries of this matrix, if you want to break it up in a nice way, what you do is you write it out, you break it into two like this, where you take the even numbered, indices here. Okay, and here you go 1, 2, 3, dot, dot, dot. You know, so here you go with j n over 2 plus j, and here you look at 2k and 2k plus 1, right? And then what we said is, if you look at these matrices now, okay, so what are we doing here? Well, what we are doing is exactly what we did on the, in the previous slide. What we did is we are multiplying these two polynomials and we separated them out into the evens. So this is the even polynomial consisting of the even degree terms, and these are the odd degree terms, A1, A3, dot, 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 right? Exactly what we did so we are just trying to make sure we multiply, we are evaluating the polynomial at x and minus x, and doing it by even powers, odd powers. And then what we said is this becomes ft n over 2, ft n over 2, omega to the j ft n by 2 minus omega to the j ft n by 2. Okay. And then we said we can do this multiplication very fast by divide and conquer, you know, because we have the same terms over and over again, right? So hopefully this ties the two pictures together for you. We are doing exactly the same thing in matrix notation, right? Okay, so now, okay, so now let me write this matrix that I've written down, you know, so let's use the notation from the book for it. Let's call it omega sub m sub n of omega. So this is this matrix whose j kth entry is omega to the jk. Now, so what we're saying is m sub n of omega times a naught, a1. You know, if we start with the coefficients, we get the values at 1 omega to the n minus 1. Now we want to go the other way. We want to go from here to here. So what should we do? Well, clearly we should say m sub n of omega inverse. We should multiply by the inverse of the matrix. And then if we apply that to a of 1, a of omega to the n minus 1, we'll get a naught, a1, a n minus 1. Okay, so how do we multiply by the inverse of the matrix? So it turns out there's something very nice that happens. The inverse is just 1 over n times this FFT matrix, except instead of using omega, so here's our complex plane, real, imaginary. Here was omega. Instead of using omega, we use omega inverse, 1 over omega, right? Which is also the complex conjugate of omega. So, you know, it's just whatever it was, you know, if this was 2 pi over n, then that's minus 2 pi over n, okay, at omega inverse. Okay. So this is something really nice about this FFT matrix. Now, okay, so this is something that you know, you can sort of check very easily, and you know, another way of saying it is that. So let me just write it down here. If you take m sub n of omega times m sub n of omega inverse and multiply by 1 over n, you get the identity matrix, right? And okay, so this is something that you know, it turns out there's a very nice geometric reason that this happens, and you know, to see that, you know, what you do is you look at m sub n of omega, and actually, you know, I said there's this factor of n that you have to divide by. You know, it's sort of nicer to, if you want to think about it geometrically, it's nicer to divide everything by 1 over square root n so that it maps unit vectors to unit vectors. And now, what this n by n matrix does is it maps. Okay, so this is something I'm saying only for, you know, this is, so I'm sort of giving you an advanced view of the subject, which, you know, you shouldn't by any means feel like you need to know. but those of you who follow it, it'll be, it's sort of a nice thing to know about. So let's think about what this matrix is doing. It's sort of operating on these n-dimensional vectors. And so, so here, this is our basis for the vectors. We have the unit vector in this first basis direction, the unit vector in the second basis direction, and the unit vector all the way in the nth basis direction. And now what this matrix does is it's some sort of linear transformation. So what it does is it maps each of these vectors to a different vector, right? And if you're given, moreover, any other vector in this space, in this n-dimensional space, it also maps it somewhere else. That's what we are trying to figure out when we do the Fourier transform. We are just trying to understand, what does this vector a0, a1 through an minus 1, where does it get mapped to? Now it turns out that this transformation, this FFT, this Fourier transformation is special. What it is it's a rigid body rotation of this space. So what it does is it just takes this space and it rotates it in some way. Okay, so each of the basis vectors sort of get taken somewhere else, and as the space is being rotated, every other vector also gets rotated along with it. Okay? And so, such transformations are called unitary transformations. And what we are saying when we say we want to do the inverse Fourier transform is we want to undo this rotation. It turns out that when you have a unitary transformation, there's an easy, if U is a unitary transformation, then sort of the way to undo it, U inverse, is almost like U transpose, except that you have to take the complex conjugate of all the entries. So it's you just take all the entries. So you take U, which may be a0, a1, a2, a3, and you take the transpose. So you're taking a0, a2, a1, a3. So you just take, you just flip the matrix over across the diagonal, and then you also take, if these are complex numbers, you take their complex conjugates as well, and that's your inverse of the matrix. And so that's all we did in this last slide when we said the inverse is exactly the same, the Fourier transform matrix evaluated at the inverse, or the complex conjugate of omega. Okay, so you can, the easy way to think about it is it's just the same matrix with omega replaced by omega inverse. If you want to know sort of the easy big picture, the sort of the more mathematical picture of what's going on behind the scenes, this is what's going on behind the scenes. This is why it's easy. Okay, let me see. If I have a couple of minutes, let me just see what the time is. So I have a couple of minutes. So let me just say a couple of more minutes of something, and then I'll stop for questions. So let's see. Okay. So here's the way to think about it. So suppose we want to unwind all this into a circuit for computing the Fourier transform. So what would we do? So suppose we are doing it for 8 inputs. Polynomial of degree 7. So what we do is, first we would sort the inputs into even and odd. So we'd have A0, A2, A4, A6, and then A1, A3, A5, A7. We'd feed these into FFT sub 4. We get outputs. Similarly, we take these we'd feed these into, okay. And then remember what our rule said? Okay, so I'll just remind you. Okay, so the jth output here on top is going to be the top output plus the n over 2 plus jth output. So it's the one from here. And you're going to add them. But before you add them, you multiply this by omega to the j, right? And down here, what you do is you subtract them, except you take the, oops, sorry. So I shouldn't have done that. I should have said this output. What we are doing is we are multiplying it by omega to the j, right? And similarly, we'll do this for every j. So for this one, we'll go ahead and we'll multiply by omega to the, so j being 5. So we are, is it 5? Oh, sorry, 0, 1, 2. Maybe it's omega squared, right? This would be omega to the 0. And we take the corresponding outputs and over here we'd add them. Here we would subtract them. So is it clear what I'm doing? I'm just saying, look, you take the corresponding outputs and you add after multiplying by the lower one by some suitable power of omega. So omega to the 0, omega to the 1, etc., and so on. Okay. And this whole thing, this whole circuit that we have here, this box would be FFT sub 8. So the way you get the FFT on 8 inputs, for degree 7, is you divide up the inputs, you do an FFT on the even ones, the odd ones, and then you combine them pairwise through this addition and subtraction, right? And so you get your 8 outputs like this. So I meant to do it for all 4 of them. Right? Okay, so that's the way you get your 8 outputs. Now, of course, you can unwind each of these FFT boxes as well. And so if you do this unwinding, you get, what's called a butterfly network. So, you get this, each of these, if you look at them in the right way, it should remind you of a little butterfly. And so it's a network of butterflies, right? And now you could also ask, well, in which order should you be giving the inputs? So we took the even ones here and then the odd ones there. And then among these, we'll take the even and odd and so on. And so if you think about it, what's happening is, these, if you write them out in binary, then these are all the ones which have a least significant bit of 0. And these are all the ones with the least significant bit of 1, and so on, right? So it's as though you're writing out the binary numbers in opposite order. So you start with 001 or 000, and then you go with 001, 010, 011, right? So this way, all these the first 4 numbers have least significant bit equal to 0. And then you go to 100, 101, 110, 111. So what I'm doing is I'm doing a bit reversal. I'm reading these bits as though this is the least significant and that's the most significant. And that's how I got to, that's how you get the input. So this one is A0, that's A4, right? In binary, that's A2, A6, and so on. So you start with all the bits reversed. That's how you feed in the inputs. And then you unwind this, these FFTs, and you get the entire circuit, which looks like this. And then the outputs, of course, are in the correct order, right? So you start with bit reversed inputs, you feed them through this network, and you get the outputs in the correct order. And as you can see, there are going to be log n levels to this circuit. And you're doing, and the height of this circuit, you know, the width of the circuit is n. So they are exactly n log n gates, right? The amount of work being done here is n log n, but it's done in this very nice manner, which is just, you know, it's completely laid out for you. Okay, so let me stop here with the lecture and ask if there are any questions.
Oh, Professor.
Yes.
Like for inputs, we order it, like we sort the order by like the evens and odds. Is the matrix, do we have to sort the matrix column as well, or is it already designed to work that way?
Well, we've actually, you know, we've actually figured out. So let me remind you when, oops, sorry, it's a little ways ago. So when we, you know, when we did this decomposition of the FFT matrix, right? When we Fourier transform matrix, we already took into account that we had rearranged the columns, right? So that's how we understood that in order to apply this matrix, you had to apply the Fourier transform on the first n over 2 entries and the second n over 2 entries separately, right? So the reorganization of the matrix was implicit in our understanding of, or explicit in our understanding of what the matrix looks like.
So if we were to like code it out, it would be like, we would have to like reorder everything, right? The matrix and the input.
No, because remember what we are doing is we are saying, once we reorder the columns, we get to break up the matrix into these pieces. So we never actually multiply, we are never multiplying this n long vector by a matrix, right? We are saying we break up the vector into 2 pieces, and then to apply this matrix, the n by n matrix, it's sufficient to apply an n over 2 by n over 2 matrix to the first half and the second half separately, right?
Oh, okay, I got it.
Right. So implicit in the way we are solving it, we are assuming that the columns have been already, you know, there's this notional matrix whose columns were rearranged, but then we never multiplied by it. We said, actually, we can break it up into these smaller matrices, and that smaller matrix, lo and behold, happens to be Fourier transform of size n over 2. So that's all we need to apply. But then when we go to apply it, we again say, look, we have notionally rearranged all the columns. So we broke it down into these smaller matrices, which happens to be a Fourier transform on n over 4. So we break up our vector into 2 pieces. We apply this Fourier transform of n over 4 to that matrix, right? And we just keep going all the way. It turtles all the way down, right? Until we get to the base case, in which case we know how to multiply explicitly.
So the 2 sub-matrices are ft n over 2, and then that multiplied by omega j,
yeah.
right?
Yeah,
okay.
Right. Well, actually, so in fact, the submatrices all look like ftn over 2. So we just need to multiply the top by ftn over 2 and the bottom, you know, the lower half of the vector by ftn over 2, right? And then we just given the answer, then we glue the solutions back together by multiplying the jth entry by omega to the j and adding and subtracting and so on.
Oh, could you?
Professor, I think one question that was asked on Piazza is, why is 1 over square root n times n omega a rigid body rotation? That's not.
I'm sorry, say this again.
If you go back to one of your previous slides, you mentioned one of the expressions was a rigid body rotation.
Oh, the rigid body rotation, yes,
yeah.
This one, yes.
Yeah.
Okay, so here what I was saying is, you know, your matrix, if you scale it by 1 over n for convenience, so that now it maps unit vectors to unit vectors. So this is an n by n matrix, right? Yeah, it's an n by n matrix. When you apply it to an n-dimensional vector, okay, this is some linear transformation. So what it does is it takes your n-dimensional space and it does some linear transformation to it. So what does this linear transformation look like? So in the case of the Fourier transform, if you suitably scale it, then what it does is it always maps unit vectors to unit vectors. Also, it preserves angles between vectors, right? So if you have a unit vector and if you compute the Fourier transform, it'll always be a unit vector, with this small normalization. The other thing you can say about it is, suppose you have two vectors and they make an angle theta with each other. You apply the Fourier transform, it's going to map this vector somewhere and that vector somewhere else. But wherever it maps them to, the angle between them is guaranteed to still be theta. So whatever the original angle was, it's still going to be the same angle. Okay, so that's the sense in which what it's doing is it's doing a rigid rotation of the space. And so, all we need to do in order to understand the action of this matrix is to understand this rotation of the space. And now, if you want to undo this rotation, that's the inverse transformation, right? So going from coefficients to values, it's this rigid body transformation. It's this rotation of the space. So you start with your original polynomial, you rotate the space, you're at the values at the roots of unity. Now you want to go back. So what should you do? Well, you have this rotation, you want to undo the rotation. So you want to know what's the matrix that corresponds to undoing the rotation. It turns out that that matrix looks almost exactly like the Fourier transform matrix. And that's true in full generality, in the sense that whenever you have a matrix that represents such a rigid body rotation, these are called unitary matrices. Okay? So then if you want to undo its effect, essentially what you do is you take the matrix and you take its transform. Right? So you take it and flip it around the diagonal. Okay? Except you don't just do that, you also take the complex conjugates of all the matrix entries. Right? So that's why you call it not the transpose, but the conjugate transpose. So it's denoted by this dagger, right? Because you're also conjugating the entries and you're also doing a transpose. And so what we did with the FFT matrix is, if you do this, if you transpose it and if you conjugate all the values, then you realize it's still the FFT matrix, except omega is replaced by omega dagger, or sorry, omega conjugate. And omega conjugate is the same thing as 1 over omega, right? So that's all I was saying there, that you can either sort of work through the mechanics of it, and you can sort of see that, in fact, when you take m sub n of omega and multiply it by m sub n of omega inverse, and you put this normalization 1 over n, you get the identity matrix. So that means that we figured out what the inverse is. Or you can appeal to this bigger geometrical picture, and then you sort of know how it works out. Okay.
So if we do, oh, go ahead.
No, it just relates to like syntax.
I'm sorry.
Oh, I was curious about so like, what does omega like represent? Does it just represent like a vector of complex numbers?
What is omega? Okay, what's omega, right? So omega. So let's see what's so if you want omega, which is a primitive 8th root of 1, right? Then it turns out it's something like omega equal to 1 plus I over square root 2. It's this complex number.
I see. So it's a primitive nth root.
Nth root of 1, right?
Okay.
So if you want omega, which is a 2nd root of 1, then it's just omega equal to -1, right? as we go to, you know, n, which is higher and higher, we have to go into complex numbers. You know, already at the 8th root, it looks like this. You know, if you want omega, which is a 4th root of 1, then it might look like omega equal to I.
Okay. So what does it mean to get the inverse of omega? I wasn't quite sure. Is that
I'm
just a
sorry?
complex omega?
Yeah, so if this is omega complex conjugate, which is also 1 over omega, right? Omega to the -1, which you can write as 1 over omega. This is just 1 minus I with square root 2. Okay, so let's just verify this. So let's take 1 plus I over square root 2 times 1 minus I over square root 2. What do you get? Well, you get 1 plus 1, 1 times 1 is 1. This is minus I squared. I squared is -1, so we get plus 1. Okay, plus I minus I over 2, right? So this is just 1. Right, so I was trying to say this is like 1 over that, right? The product of omega and omega bar, you know, the conjugate of omega is just 1. Yeah.
Thank you.
Yeah, sure.
I was wondering, so if 1 over root n mn is a rigid body rotation, so we can inverse it, right? Why don't we scale it by 1 over root n? Why are we scaling it by 1 over n instead for the normal?
Well, you know, so here what we did was when we computed the Fourier transform, we didn't divide by square root n, right? So you see, what I was suggesting was, you know, you have to divide by, you know, in the round trip, you have to divide by n. If you want to go do FFT and come back, you have to divide by n somewhere. So you could either say on the way forward, I'm just not going to divide. And on the way back, I'll divide by n. Or you could say, regardless of whether I go forward or back, I'm going to divide by square root n. It's the same thing, right? Now, if you want to preserve the geometry, it's better to divide both while going forward and going back. And then you divide by square root n on the way forward and square root n on the way back. So in the round trip, you're dividing by n. But the nice thing about that is that, you know, because when we start from a vector, you go forward, you do something, then you come back, you want to come back to the same vector, right? So what we are saying is, if you divide by square root n on the way forward, then if you started with a vector of a certain length, the length is going to be preserved when you go forward. And then when you come back, it's still preserved. So you come back to the same length, the same vector. Whereas if you don't divide by square root n on the way forward, right? And then you come back, well, now you're going to have to divide by n to you know, your vector is square root n bigger. And then you come back, it's another square root n bigger. So you'd better divide by n at this point.
So then,
right? Does it make sense?
Yeah, so then why do we do 1 over n instead of 1 over root n if it's more advantageous because we get to like keep all the properties if we just do it?
Well, you know, I don't know, it's just convention, right? So normally when one does Fourier transforms, depending upon which application, right? So in electrical engineering, you always, or in, you know, in many subjects, you always do it without dividing while going forward, and you divide by n on coming back. When you're doing quantum mechanics, you always want unit vectors, so you divide by square root n while going forward and back, right? So it's nicer, the picture is nicer. So depending on whether you want a nice picture or whether you want to do fewer divisions, right? So it conserves work if you do it only on one side rather than both.
Yeah, so then in this case, it's not going to be the same size going forward because we're not dividing by root n,
Yeah.
forward. Right?
Yeah.
Okay.
Yeah, so the vectors, if you start from a unit vector, you'll get a longer vector on, when you do the Fourier transform. And then when you come back, you'll come back to the same one.
Okay.
Hi, Professor. I was hoping we could very quickly touch back on the circuit diagram that you showed. I think I'm rather clear on both the matrix and like just the polynomial splitting forms that we've looked at so far. I'm just a little bit unclear as to how the parallel computation is working in the circuit diagram.
Okay, all right. So let's think about it. So what are we doing? Well, we are given this n-dimensional vector to begin with, a0 through an minus 1, right? So this is our n-dimensional vector. We get to split it into two pieces, right? The evens and the odds, right? Then what do we do? What does the algorithm say? The algorithm says, next thing you do is recursively do a Fourier transform, right? So we do a recursive Fourier transform on the first four and the recursive Fourier transform on the second half, right? Now, once we get this recursive Fourier transform, now we have to figure out what the top half of the vector that we output looks like and what the bottom half looks like. So you remember what the top half looked like. We took the Fourier transform of the even part plus omega to the j times the Fourier transform of the bottom half. So that's what I'm doing. I'm saying the first entry is going to be the Fourier transform of the top half, the first output of the Fourier transform of the top half, plus omega to the j times the first entry of the Fourier transform of the bottom half. Right? That's what I did here. I took the first entry, and I took this up here and I added them and I said that's the output. Right? Before adding it, I multiplied by omega to the 0. What about the bottom half? We said, well, that entry is you take the first entry of the Fourier transform of the top half minus omega to the j times the first entry on the bottom half. That's what we are doing here, right? And then you do the same thing for the second entry and the second entry here, except now you multiply by omega to the j. J here is 1. So that's all that changes, and then you keep going. You put minus here, right? And oops, sorry, shouldn't have done that, but okay, yeah, like that, and then like that, and here you'd get a plus, right? So you just get these, on these corresponding wires. You put in your butterflies. You put in plus, minus, omega to the j. So here you'd get omega to the 3. Okay, and then you unwind. Okay, so that's your circuit, except now the recursive fast Fourier transform is sitting here as a box. So what you would do now is unwind this box further. So you get one more layer of butterflies, and then you'd get FFT2 right here. But you'd also take these and you'd sort them again. So you'd get A0, A4, A2, A6, right? So you'd swap them out, right? And similarly out here, you'd do A1, A5, A3, A7, whatever it is. You'd unwind this recursion further. You'd get one more level of butterflies, and then you'd get FFT2, and then you'd unwind that again, and then you're down to.
Oh, I see. And it's because of that continual resorting when we're winding ourselves back. That's why we're sorting based off of that least significant bit as opposed to the most significant.
That's right. Exactly.
Okay.
Exactly. So at this first layer, what we did was we sorted so that all the zeros were here, all the ones are here, right? Now the only index we have is this piece. So in this FFT4, recursively, we are just dealing with this top half, right? So now we want the zeros to be on the top and the ones to be on the bottom, right? And then when we get to the last level, we want the 0 to be on the top, 1 to be on the bottom, because this is what, now each of these has been split up further. So now when you look at it, what's happening is it's as though this became the least significant bit, that's the most significant bit. right? So we are going backwards when we read this number. That's the least significant, that's the most significant. So when we are counting, it's as though we had a counter where we start from all zeros, and the one, this one increments, and then it increments again, so you get a carry, so 0, 1, and it increments again, and so on. So that's how you increment these. And so when you read it off, it's A0, A4, A2, etc.
Thank you. That clarifies it.
Mm-hmm.
So then if no one has a question, I'll just jump back in again. I'm still a little bit unclear as to why we're doing that dividing by 1 over n in our van der Waals matrix, because as far as my admittedly flawed understanding is, every single one of our unitary roots is of size 1, because that's the whole idea.
Okay,
right?
so good. Let's look at it. Okay, so so what does our matrix look like? It was 1, 1, 1, 1. Let me just do 4. We had 1 omega squared, omega cubed, 1 omega squared, omega to the 4, omega to the 6, 1 omega cubed, omega to the 6, omega to the 9, right? That's what it looked like, something like that. Mm-hmm. Now say we had 1, 0, 0, 0, right? So that's our unit vector. What does this look like? Well, what's the first entry? You just get 1, 1, 1, 1. Right? This is manifestly not a unit vector. Right? The length of this vector is 1. What's the length of this vector? So this length, Euclidean length is 1. This length is 1 squared plus 1 squared plus 1 squared plus 1 squared square root. So it's square root of 4, which is 2. Right? So if you want to make this a unit vector, you had better divide by 2. Right? Square root of 4. So always, if you want to preserve the length, you've got to divide by 1 over square root n. Right?
But why are we particularly interested in preserving the length here?
Well, it's just nice to think about it, right? That if you want to understand the structure, it's nicer because then you can say, isn't it nice to say, I really can picture what it's doing to space. All it's doing is it's rotating it. Whereas this way, if you look at this transformation, what it's doing is, well, it may be rotating it and then magnifying everything. That's a bit more complicated, right? So if you want to understand what it's doing, then simplify it and just multiply by 1 over square root n. If you want to do the computation, then you don't want to keep multiplying by 1 over square root n each time, right? So if you're planning to do a Fourier transform and then eventually do an inverse Fourier transform, then you may as well do the division once, right? So if you always say, well, going forward I won't divide. When I come back, I'll divide by n. Nobody will be any the wiser, right? You're always going back and forth, so it's completely fine, and it's much better for you because you only divide once instead of twice, right? So if you want it to be conceptually the right thing, then you always divide because it doesn't cost you. What costs you is keeping a nice picture of what's going on. Whereas if you're actually computing, then you only want to divide once.
So then in our FFT process, when we're doing that sort of coefficient to interpolation process, we're accepting the magnification, and when we're transmitting it back from our value representation to our coefficient representation, then we're getting rid of the magnification for both transformations, right?
Well, actually, in terms of going from the coefficient to the value representation, dividing is the wrong thing to do, because the polynomial itself, so in other words, when you're when you want to go from if this was a polynomial, if our polynomial was a of, this is the polynomial a of x equal to 1, right? That's what this polynomial is, right? And now if you want the vector a of 1, a of omega to the n minus 1, well, this happens to be the you know, that's what that you know, that's what it looks like, right? Because the value representation is this polynomial is 1 at every point x, including 1 omega to the n minus 1. So it's clearly the case that when you go from the coefficient representation to the value representation, you know, you are expanding things out, right? You shouldn't be dividing by square root of n.
Mm-hmm. So then when we're going
in terms
back,
of this interpretation,
mm-hmm.
yeah.
But then when we're going back from our value representation to our coefficient representation, why does the scaling then become necessary?
Well, because if you write the inverse transformation, then you know, I said the transformation is you take the same matrix, you turn it on its head, you know, you transpose it, and when you transpose it, but then you also write, and the transposition doesn't do very much to it. It's, you know, it's sort of okay, but then you write etc. If you take this and you multiply it by this original matrix, etc., right? Then you would get the, if you work it out, you'd get the matrix n. Right? That's the matrix you'd get.
Mm-hmm.
Right? So meaning if you go from here to here and then come back, you'd get a of x equal to not 1, but you'll get n.
Mm-hmm.
So if you want to come back to the same polynomial you started from, then you had better put in a 1 here, 1 over n here, so that you get identity.
Okay, thank you so much. That makes a lot more sense.
Yeah. Okay, sure. How are we doing for time? Yes, go ahead. Sure. Yes,
I
please.
just have like another extra question. So in this case, because we're multiplying everything by 1 over n, we can just get our, when we're going back from our value representation to our coefficient representation, we can just use the matrix we had before, the scaled matrix, and then with our scaled value coefficient representation, we can just multiply that by 1 over n to get our true original.
Yeah, well, I mean, the way to think about it is that this becomes the inverse Fourier transform, right? So you take your fast Fourier transform circuit, you replace omega by the conjugate of omega, right? Meaning not e to the 2 pi I over n, but e to the minus 2 pi I over n. And then you take the results you get, you divide by n, and you do it. That's your inverse Fourier transform.
And so this also means that we could actually also, you could choose any scaling coefficient as long as their product is 1 over n, right?
I'm sorry. Can you repeat?
Instead of like 1 over the square root of n, instead of using 1 over square root of n to scale, we could use, for instance, like the 1 over or n to the negative. I'm trying to think of I'm trying to think of two numbers that would apply to the
okay.
number.
So look, here's all I was saying. You know, let me just say it in a simple way, right? So you had to have a 1 over n here so that you get identity instead of n's here, right? Now you can get that in many ways. You could do 1 times 1 over n here and 1 here, right? Or you could do 1 over square root n here and 1 over square root n here, right? So you could have the Fourier transform be defined with a 1 over square root n, and you could have the inverse Fourier transform defined with 1 over square root n. So these two numbers give you 1 over n. So it doesn't matter how you do it, right? And so what we did was we said the Fourier transform is defined with the coefficient of 1 here, right? And the inverse Fourier transform is defined with this coefficient of 1 over n. But if we wanted to, we could put any other coefficient here as long as we put, 1 over n times, whatever, how do you say, so that the product of these two should always be 1 over n. That's all we need.
Yeah.
So
for instance,
so
like n over
that's
1/3, negative 1. Oh, n to the negative
yeah.
1/3 is n over negative 2/3. Okay. Thank you.
Right. Right. So that's all that we need to ensure. But okay. But the convention is we just always do the Fourier transform like this and the inverse Fourier transform with the 1 over n. So that's what we do for computational purposes. Right?
That makes sense.
Mm-hmm. Okay. Good. Okay, so if there are no more questions, I think we are at the end of the office hours. Let's see. I should just check. Oh my goodness. Okay, so are there any more questions? I can stay. I think it's 5:30 already, but if you have a couple of more questions, let me just ask people. How maybe I should. How well do you okay, let me first stop sharing the screen so that just to make things a little bit easier. Okay. And
Professor, you're still recording the lecture.
okay, so somebody else okay, let's stop recording. And let's see, did it stop?
No, I can stop the recording now.
Okay.
Yeah.
And stop share. Okay, good, much better. All right. Okay, good. Are we basically okay? So